This video takes a look at three examples, three different ways that force can be used to calculate work. This first example deals with a function of force, and notice how the variable in the force function is not t like we've been used to working with. In this case, force is given as a function of x, and again that's important because work has to do with force and how far an object moves during a certain phase of its motion. To calculate the work, we are going to basically use the integral that I showed you earlier in the earlier video. I'm just going to state this, that instead of using it in terms of r, it's going to be in terms of x. You can change r into x or y or z, whatever variable makes sense. So we're going to integrate this, but it's going to be an integral where we know the bounds. So writing our force function in here, 4x plus 6x squared, and we are integrating with respect to x. Again, that's a formality, that dx. And then our bounds are from 0.5 meters to 1 meter. And so we'll go through the process of integration. Remember that we're going to increase the exponent and then divide by the new exponent. So this would end up being x to the second divided by 2, so that would end up being 2x squared. And then the 6x squared, we would end up increasing to x to the third, divide by 3, so 2x cubed. And then we're going to evaluate that from 0.5 to 1. And so we need to take 2 times 1 squared plus 2 times 1 cubed, all minus 2 times 0.5 squared plus 2 times 0.5 cubed. Calculating this out comes out to be 3.25 joules. And so this would represent a change in the energy. Again, this is the work being done, but how we'll use this is it will represent by how much the energy changed comparing the energy at 0.5 meters to the energy at 1 meter. Another way that force information can be given to us is using a graph. So again, this is a situation where the force is changing, so we can't just use the simple version of work equals F times X. We're going to have to basically integrate, but whenever we have an integral symbol, we are able to also use the area of a graph that displays whatever this variable is, the force in this case, on the y-axis, and then in this case x on the x-axis. So any sort of integral that you have in terms of an equation can indicate that area is represented by, or that area represents a certain quantity. So when we find the area of this shape, it will determine the work being done as this object moves from x equals 0 to x equals 11 meters. So the area of my rectangle that I've marked out here would just be 40 newtons times 6 meters. And then the area of this triangle would be 1/2 times my base times my height. Again, 40 newtons is the height, and the base is 5 meters. So putting that all together, we end up with 340 newtons times meters. Again, that is a joule. That is the amount of work that is being done as this object moves from 0 to 11 meters with this changing force. Again, what we'll use that information for is this will be set equal to the change in the object's energy. So it'll allow us to sort of use the same sorts of ideas we did with conservation of energy, but having this additional amount added in. All right, our final example is something that probably looks a little bit more familiar. Here we do have a situation where there is a constant force of 20 newtons. And so in this case, our kind of formal looking equation, again, that's what's written on our formula sheet, can be rewritten as just a constant force times x times the cosine of the angle between those two things. I'm going to go and just do a quick sketch here. So we have this suitcase, and we are pulling it with a strap, and the strap is inclined upward at an angle of 40 degrees measured to the vertical. Okay, so that means that this angle is 40 degrees. Got to be careful there because the motion is this way and the force is this way. So this is actually the angle that I need in order to use this equation. So I got to make sure that I use 50 degrees in my calculation. So our force is 20 newtons, and the distance that we're moving the suitcase is 100 meters times the cosine of 50. And that comes out to be roughly 1285, or about 1300 newtons times meters. And again, when we're talking about energy, we change that newtons times meters to joules. So again, this would then represent the amount of energy that is being transferred to the suitcase. So we probably end up setting that equal to the change in kinetic energy or something like that.